All right, hello everyone, and welcome to lesson 2.3. Today we're going to be talking about derivative rules, the first of our derivative rules. We've now seen that there is this thing called a derivative that measures the slope of the line tangent to a graph at a specific input value. Now, it would be really frustrating to have to evaluate those limit definitions over and over and over again for each time we want to take a derivative or find a general derivative. It turns out, as you might have noticed from some of the things we've already done, that there are some patterns. And so typically we use these derivative rules, these patterns, to help speed up the process of finding what that general derivative equation looks like. To get started, go ahead and do this now. Write the following expressions as expressions not in fraction or radical form with one exponent. For example, 1 over t squared is t to the negative second power. Pause the video and go ahead and do that. All right. Let's go ahead and take a look. This first one we could rewrite as t to the negative 2/3 power. Taking 1 over t to the 2/3, bringing it out of the denominator, that t to 2/3 out of the denominator would make our exponent negative. Here we have a square root and an x to the 5th, so this would be x to the 5 over 2. I remember that the root stays underneath the fraction like a root stays underground. Square root, so it's over 2, and x to the 5th stays on top. Here we got kind of the combination of those things, 1 over the cube root of v squared. So this will be v to the negative, since it's 1 over, we're taking it out of a denominator. V to the negative, our power on v is 7, so I'm going to write 7, and our root is 3, so there we go. Now this skill is actually honestly one of the ones that will slow people down the most. The derivative rules people will remember, but a lot of people forget to rewrite things so you can easily take your derivative. So I encourage you, whenever you see power things like this that are written as fractional powers or fractions or radicals, rewrite them so you can just see it as a simple base to some exponent. All right, let's take a look at these derivative rules that we'll be using all year. So at the start here, the rules start off really simple. The constant rule. The derivative of a constant function is simply 0. This is, if c is a constant, then the derivative of c is just 0. This makes sense because remember the derivative measures the slope of a graph. And if we have a constant function, for example, the function f of x equals 2, that is a flat line at 2, and the slope of that graph is 0. All right? So the derivative of any constant is just 0. This makes sense since the graph of a constant is horizontal, which means it has a slope of 0. So, as examples here, if y equals 7, then y prime would be 0. 7 is a constant. If f of x is e squared, remember e is not a variable, e is a number, and that number squared is going to be some number. I don't know what the number is off the top of my head. It's going to be whatever 2.71-ish squared is. It's going to be some number, but the derivative of that, since it's just some constant, will be 0. All right? And same thing here, if s of t is negative 8 is a constant, so its derivative is 0. S of t is some flat line at a value of negative 8. P of t is 2 pi cubed. Pi is just some number, right? So 2 pi cubed is just going to be some number, and the derivative of that, dp dt, is going to be 0. Relatively simple rule, but one that sometimes trips people up and they forget about. But don't forget pi, e, those are constants. Next up on our plate is the power rule. The power rule is probably the one that most people, even if they never take calculus again, will remember the power rule. All right. The power rule says this: if n is a real number, then the function x to the n, so x is our variable, n is some real number, could be positive, negative, fraction, but it's a real number, is differentiable, and its derivative, the derivative of x to the n, is n times x to the n minus 1. In other words, if we want the derivative of x to the n, we bring down the power, we multiply it in front, and then we subtract 1 from the power. This gives us a pretty nice, easy to use pattern. If g of x is x to the 5th, g prime of x, I'll bring down the 5, I'll put it in front, I then multiply it by, so that's n times x, whatever that variable was, to the power, but minus 1. There we go. There's the derivative of x to the 5th. This applies even if we have to rewrite things so that we can see the powers, okay? And any of these things we see today can all really be boiled down to things revolving around the power rule. We just have to be able to rewrite them so that we can see those powers. 1 over t is really t to the negative 1. And I can take the derivative of this. I can call it h prime of t. and the derivative of h prime of t, I would bring down that power. That'd be -1 times I keep the base, and I subtract 1 from the power, -2. All right, if you want to, we can clean this up. T to the -2, that is going to be something over t squared, and there's a -1 in front there, so it's -1 times 1 over t squared, so that would be the simplified form. We could do this one here too. We could go ahead and rewrite 1 over t to the 3/4 power as t to the -3/4 power, and find its derivative. P prime of t is going to be, I'll bring down that power that I see, -3/4. I'll keep the base, but I'll subtract 1 from that power. Now you might go, oh, I'm a little afraid of subtracting fractions. Don't worry about it. -3/4, if we want to subtract 1 from it, is the same thing as subtracting 4 over 4. So it becomes -7 over 4. If you want kind of the quick way to do this, the quick way to subtract 1 from a fraction like this is just subtract the denominator from the numerator. So -3 minus 4 gives -7, and then keep the same denominator over 4. -7 over 4. Remember in my class, you don't have to simplify any of these free response questions. You can just leave them like this. If you wanted to, we could rewrite p prime of t in this case as -3 would stay up in the numerator, 4 is in the denominator, and then t to the -7/4, we could flip that into the denominator and lose the negative sign, and there we go. All right. I want you to go ahead and give D, E, and F a shot. Pause the video and try D, E, and F, please. All right, here we go. We want to take the derivative of q of t, so q prime of t is going to be, well, q of t is square root of t. That's the same thing as t to the 1/2 power. Take the derivative of that, I'll bring down the power, I'll keep the base, and then I'll subtract 1 from the power. So this would be 1 over 2 minus 2 over 2, which will give me -1 over 2. All right, or if you simplified 1 over 2, and then t to the -1/2, that'll go into the denominator as t to the 1/2 power, which I guess we could say is 1 over 2 square root of t. All right. R of x is x to the 2/3 power, so r prime of x is going to give us, well, we'll bring down the power, 2 over 3, x to the, then we'll subtract 1 from the power, so 2 over 3 minus 3 over 3 will give me -1 over 3. All right. Simplified down, that'll give us r prime of x, r prime of x then will be 2 over 3 cube root. That should be, wow, that got real weird there, huh? Okay, let's do 2 over 3, and that'll be times the cube root of x, if we want to simplify it all the way back down to some sort of radical there. All right. And y equals 1 over cube root of t. Well, let's rewrite this so we can see the power. That's always our goal here. T to the negative, it's a cube root, so it's -1/3 power. So dy dt, or y prime, there's different ways we can write that, equals, I'll bring down the power, I'll keep the base, and then I'll subtract 1 from the power, -4/3. Now keep in mind, all these things we're finding, all of these final answers, these derivatives are the general derivative. They will tell us the slope of the original function at any t value or x value or whatever we plug in. All right. Again, the value we plug into the derivative, when we evaluate that derivative, will tell us the slope of the original graph at that input value. All right. These are all just shortcuts for those limit notations we were doing in class. It's a lot quicker, huh? All right. Next up, the constant multiple rule. If f is a differentiable function, we can take its derivative. We'll get into more details about what differentiable really means later on this unit. And c is some real number, so c is some real number. Then the derivative of c times that function is equal to c times the derivative of that function. In other words, the constant, whatever that number is multiplying some function, we can kind of just ignore, take the derivative like normal, and then multiply it back in. Some people will talk about this like it's factoring out. We're not really factoring out. We can kind of just multiply that constant by whatever the derivative actually is. All right, so let's find the derivative and use the correct notation. Here's the sort of long way to think about this. If I want to take the derivative of g of x, which is 3x squared, I could think about it like this. Well, 3 is a constant, so I'm going to leave that out in front by itself. And I'm going to multiply it by the derivative of the variable thing, x squared. That's a power rule thing. I bring down the 2, I keep the x, I subtract 1 from 2, which gives me 1, and there we go. And then I can simplify that as 3 times 2, which will give me 6x. Basically, ignore the coefficient, leave it there. Take the derivative of x squared, which is 2x, Remember, I subtract 1 from the exponent using the power rule, so now I have an exponent of 1. I'm not going to write it. And then clean it up. You might go, well, that's like a weird extra step. Can't I just multiply 2 times 3? Yes. So what I would encourage you to do, actually, for these sort of constant multiple situations is that g prime of x, we can really just say, okay, 3x squared, this is a power rule thing. I bring down the power. 2 times 3 will give me 6. I keep the base, and then I subtract 1 from the power, which will be 1, and there we go. This does require still that we simplify or rewrite things so that we can see the powers. For example, in h of t here, I would have 2. T squared is going to be t to the negative 2. And so my constant multiple rule will tell me I really don't care about that constant here of 2. I'm just going to let it be and then multiply into it. So that's the derivative of t to the negative 2. I bring down the power. It's a power rule, multiply. 2 times negative 2 will be negative 4t. And I'm going to subtract 1 from negative 2, which is negative 3. We always got to be careful with that because sometimes, and sometimes you'll even see me do it, subtracting from a negative number makes it more negative. All right? Now, apologize if I actually already have made a mistake like that. We'll always be on the lookout for that. Subtract 1 from negative 2 gives us negative 3. All right. This one, sometimes it helps also to sort of pull out coefficient fractions. 4 over 3 I can kind of pull out in front, 4/3 x cubed. And I say, this is 4/3 times x cubed. I need its derivative, so p prime of t. I'll bring down the 3. 3 times 4/3. If I kind of have a 3 that's multiplying here, 3 times 4/3 will, well, those 3's will divide away, leaving me with 4. X, the base stays the same, and I subtract 1 from the exponent squared. And there we go. If it helps, you can go ahead and write out each of the steps. 4/3 x cubed, then we multiply 3, we bring down the power, so it's 3 times 4/3 times x, and I subtract 1 from the power. If you want to write out an intermediate step before getting here, totally fine. All right. Go ahead and pause the video and try D, E, and F, please. All right, let's take a look. Q prime of t, negative t to the 5th. Negative 1 is my coefficient there, so I'll use the power rule. I'll bring down the 5, so it'll be negative 1 times 5 will give me negative 5t, and then I'll subtract 1 from the exponent. 4 square root of x, I got to rewrite that, so that's 4x to the half power. So r prime of x, I'm going to bring down the exponent. 4 times half will give me 2. I'll keep the x. Now I subtract 1 from the exponent, which will make it negative half. There we go. And y equals negative 5 over 3 x cubed. Well, let me leave the negative 5/3 as a constant there. But then this is an over x cubed, a 1 over x cubed. So let me rewrite that as x to the negative 3 power. Maybe that makes things a little easier. Let's call this dy dx, just to mix it up a little bit. We'll bring down the power. Negative 3 times negative 5 over 3 will give me 15 over 3, which will give me 5. So negative 3 times negative 5/3 will give me 5. Times, I'll keep the base, and I subtract 1 from the exponent, which will be negative 4. And there we go. That's how we apply the constant multiple rule. Always, always, always rewrite things first to make your life easier. Alrighty. Stepping it forward a little bit. If we have some function given like h of x, which is f of x plus g of x, so a function that's actually adding things together, what's kind of nice about that is if we take the derivative of the overall function, it really is just like taking the derivatives of each of the parts and linking them together with plus signs. This works also with minus signs as well. Let me show you some examples. Let's find f prime of x for each of the functions below. F of x is x cubed plus 2x squared minus 3x plus e. Basically what this sum and difference rule means is we can ignore the plus and minus signs at first and take the derivatives of each term separately and just link them with the appropriate sign. The derivative of x cubed is a power rule, so that'd be 3x, and I subtract 1 from the exponent squared. Now I see that the linking thing here is a plus, so I'm just going to put a plus, and now I do my next one. The derivative of 2x squared will be, I bring down the 2, multiplied by the 2, that's a coefficient, 4x, and I subtract 1 from the power, so 4x to the first. And I see there's a minus on there, so I'm just going to say minus. Derivative of 3x. This one's interesting. Some people get stuck on this one. This is 3x, which is really 3x to the first power. So if I take its derivative, the derivative of something like that, the derivative of 3x, which is 3x to the first power, I would bring down that exponent. 3 times 1 is 3. X to the, I'd subtract 1 from the exponent, which will give me 0. X to the 0 is really just 1. And so 3 times 1 will give me 3. This makes sense though. Think about the way a linear function works. Y equals 3x is a linear function. Its slope is 3. So the minus sign I just kind of carry down. The derivative of 3x is just 3. Because remember, derivative is just the slope. And this is a linear term. The slope of 3x is just 3. Plus e. E is a constant. And so I'm just going to leave it like that because the derivative of a constant is 0. And we can use the sum and difference even with more complicated situations that we might have to rewrite stuff. So g of x, I see maybe we can use power rule. Let's rewrite this so we can see all the powers. That first term will be x to the negative 2 plus 3x squared minus square root of x is x to the half power. Now I can do all my power rule things. So this is going to be, I bring down the exponent, negative 2x to the, I subtract 1 from the exponent. There we go. Plus I bring down the exponent. 3 times 2 is 6. X, and I subtract 1 from the exponent, so it's 1. Notice I kept that plus sign. Minus x to the half, so I bring down the half. I keep the base, and I subtract 1 from the exponent. Sometimes these signs will change. Like in this, if I took the derivative of this now, I would have to bring down the power. I'd have negative half times negative half, so you'd end up with a plus. So sometimes the sign does change if you're multiplying by like a negative exponent. Just be on the lookout. All right. And the derivative of h of x here, we have to do some rewriting first here as well. 5 over x to the fourth is 5x to the negative fourth, minus 6x to the negative 2, minus x to the 3 halves. Now some people will tell me that this is the derivative. I actually have students who will stop here. And I get the confusion to some degree, but this is actually not a derivative. What I just boxed is really actually just you rewriting the original expression. You've not done a derivative. This is equivalent to the original expression. It is not the derivative. So we have to now actually take the derivative using our derivative rules. So we take the derivative of the first term. I bring down the negative 4. 5 times negative 4 is negative 20. X to the subtract 1 from the exponent, negative 5. Now look over here. I have minus 6x to the negative 2. So if I multiply minus 6, the coefficient, by the exponent I bring down, I'd end up with positive 12. X to the, I subtract 1 from the exponent, negative 3. Minus x to the 3 halves, I bring down the power. I keep the base and I subtract 1 from the power. So 3 over 2 minus 2 over 2 gives me 1 over 2. And there we go. Again, any of these derivatives, we could plug an x value in and it would tell us the slope of the original function at that x value. Plug in an x value in here, tells me the slope of the original function at that x value. All right, pretty good job. Last few things to show you all before you turn to do some practice, okay? Let's say we actually don't know f of x for some reason. Let's say that we're just given f prime, or we know something about the rate of change formula, the derivative equation for a function. What can we do? Let's see. Well, given this derivative, f prime of x equals 3x squared plus 1, they want us to write the equation of the tangent and normal line to f of x that goes through the point 2, 5. Interesting. We've not quite seen something like this. Tangent and normal line. Let's start with the tangent line. Here's why. Well, a tangent line is connected to a derivative because remember, a derivative is the slope of a tangent line, right? And if they want us to write the equation of a line, the equation of a line, we need two pieces of information. To write the equation of a line, we need the slope of the line and a point on the line. If we have those two things, we can hammer it down. Now in this class, we are only going to be using, as a way of writing our lines, our point-slope form. We are going to use our point-slope form, which, as a reminder, looks like this. All right? Because if we have a slope and we have a point, we can just plug it in and leave it unsimplified. Remember, brilliant thing here, we don't have to simplify anything. So how do we do that? We want to write the equation of the tangent and normal line of f of x, the function we don't have, that goes through this point. We do have the derivative, and the derivative is the slope of the tangent line. So I do know my derivative, and again, when I think derivative, I think slope of the tangent line is this. So if I give it an x value, say x equals 2, it will tell me the slope of the tangent line at x equals 2. Let's find that. The derivative, the slope of the tangent line at x equals 2, will give me 12 plus 1, which is 13. All right. So what does that mean? That's like our m for our tangent line. In our tangent line world, I'll call this just t over here. I now know that m is 13. Now I have the slope of the tangent line. Do I have a point it passes through? Yes, I was actually given that point right there. So to write the equation of my tangent line, what does the line tangent to this graph at this point actually look like? It is y minus the y value of the point I'm passing through, so 5, equals the slope of the tangent line, the slope I found, which is 13, x minus the x value of the point that I'm passing through, right there. So there's the slope of my tangent line. Now what if I want, or sorry, not the slope, that's the equation of my tangent line. We found the slope of it from the derivative and then used the point we knew it passes through to write the equation of this line, and we can leave it in point slope form like this. Now the normal lines are really easy because normal lines are perpendicular. Now perpendicular, the relationship between slopes that are perpendicular is that the slopes are opposite and reciprocal of each other. So what's nice about this is actually the points stay the same. The slope simply becomes the opposite and reciprocal. Opposite being negative and reciprocal being 1 over. All right. So the slope or the equation of my normal line is just this. It passes through the same point, but it has an opposite reciprocal slope. Now if you're like, Markwalter, I need a visual for this, let's sketch one real quick. Basically what we're saying is that we have some function here, and it goes to the point 2, 5, right there. We use the derivative to define the slope of the tangent line that passed through there, and then the equation of the tangent line that passed through the point 2, 5. And then we found the slope of the normal line that was perpendicular to that point. Again, it passed through that point, so we use the same point, but the slope is opposite and reciprocal. All right. I know this is not the actual drawing, but it's just a visual demonstration of the tangent line. We found that line, and then the normal line, we found the equation of that line. The points are the same that they pass through, but the slopes are opposite and reciprocal. Well, what about this? What if we're given the picture of a derivative and we want to write the equation for the tangent and normal line to the graph of g? Now, g is not what we're given. That's the original equation. We want to write the equation of the tangent normal line to the graph of g that goes to the point 1, 3. So I have my students write this out. I want you to get in the habit of doing this. We know the point. The point it's going to pass through is 1, 3. To write an equation, we also need a slope. Now in calculus land, where do we find slopes? We find them from derivatives. Derivatives are slopes of tangent lines. So let's start with our tangent line here. G prime, the graph over here of G prime is right here. And we want to find the slope of the tangent line at the point 1, 3. So let's go to our x value. G prime of 1. Here's G prime. G prime of 1 is a value of 2. So what does that mean? When the x value is 1, the slope of the tangent line is 2. Remember, the derivative, the y value, the output of a derivative graph tells us the slope of the tangent line. So when x is 1, the slope of the tangent line is 2. Not the slope of this graph, but the slope of the tangent line to the original graph is 2. So the slope I now know is 2. My tangent line equation then is y minus the y value of the point equals mx minus the x value of the point I'm passing through. My normal line still passes through that same point, 1, 3. So the y value, ooh, I made a mistake here. Why did I do that? The y value is not 2. The y value is 3. There we go. All right, down here, sorry, should also be 3. But the slope is opposite and reciprocal. Passes through the same point 1, 3 as opposite reciprocal slope. Again, we read derivative graphs. The y value of the derivative graph at an x value tells us the slope of the original graph at that x value. So the slope of the original graph at x equals 1 is actually 2. That's the slope of the tangent line on that original graph. Nice little challenge here. For the functions below, take the derivative with respect to x. X is our variable. Treat a, b, c, and d as constants, okay? Treat a, b, c, d as constants. Let me show you the first one, then I want you to give it a shot, and that's where we'll close out. So if a, b, c, and d are constants and x is our variable, the derivative here, we just got to think of a and b as numbers. Well, that's not too bad. The derivative of ax cubed, I would bring down the cubed, I would multiply it by whatever a is, keep x, and then subtract 1 from the exponent. Minus the derivative of bx, the exponent here is 1, I'd bring it down and multiply it by b, I just have b. Then I'd have x to the 1 minus 1, so that'll be x to the 0, and the x goes away. This is a linear term like we talked about, so it leaves us with just the slope. That's what I want you to do for each one. Go ahead and pause the video and go ahead and try the next two. Find the derivatives of g and h. All right, let's take a look. G prime of x gets a little funkier, but we follow the same rule. Cx to the 2d. So this is a constant times x to some power. I bring down that power, 2d, I multiply it by the constant that's already there. I keep the x and I subtract 1 from whatever that exponent is. It looks funky. I don't know what 2d is. It's some number. So the new exponent after I do the derivative is 2d, whatever that number is, minus 1. Minus, I'll bring down the b. b times b will give me b squared. I'll keep the x and I'll subtract 1 from the exponent. For h prime of x, I can do something similar. I have a, b. I'm going to bring down d, so it's going to be d times a times b. I'll keep the x, and then I'll have d minus 1. I'll subtract 1 from the exponent after I bring it down, taking its derivative, minus, I'll bring down the exponent c, because 3 and b, those are just numbers. Same thing with a and b. That's just going to be some number. It's a constant. So I use my constant multiple rule. I'll bring down the c. I'll multiply it in there. C times 3 times b, x, and I subtract 1 from the exponent. There we go. Cool, that's our introduction to the first of our derivative rules. What I'd like you to do now is there'll be some common practice that you need to do. Please make sure you do that. It's one of the few times I'll actually require you to do certain concepts, but it's good practice on these basic rules. And then go ahead and take the check-in quiz at the end of the Nearpod lesson. Also, I highly encourage you to keep up with the optional homework. It is the best way to make sure you're actually practicing at the level you need to practice at to be ultimately successful in calculus. Thank you for those who have done that. I really would push you, if possible, to do that. There are some textbook problems to do. Also, read the example on page 120. It's a good example. And then there's some worksheets below to practice here using the rules that we've already learned, okay? They go for like 2 pages or so. 3 pages, I apologize. Oh my gosh, I forgot. It is a little longer. It is 4 pages. Please do them, but they are really quick. You'll notice that a lot of the derivative rules we've been looking at are really, really fast, okay? I highly encourage you to do those optional homework problems. Please, please, please. All right? Make sure you take care of the concepts and do the check-in quiz. I'll talk to you later. Bye.